Hello, and welcome to today's session on F-tables and basic ratios. As always, before we get started, please make sure that you have your PowerPoint lecture notes printed and in front of you so that you can take notes along the way. Today we'll be talking about something that's familiar to us, the F-tables that we introduced in a recent video. We'll get some practice. We'll do some exercises here in the video, and then we'll also repeat these or near variations on these in the classroom. After we do that, we'll move on to something new called basic ratios, and we'll have a handout in the classroom on basic ratios. We'll use basic ratios in this case for the between subject Anova, but we'll see that as we move on through the semester, we will return to the idea of basic ratios several times. Finally, in the classroom, we'll actually do the independent samples Anova in a software package, SPSS, although we won't do that here today in the video. So let's begin by repeating something that's a little bit familiar to us, but we'll get some more practice with it. These are the F-tables, and we'll do some exercises with these. For those of you who are going into any kind of science-related career, there's a good chance that you're going to be looking at Anovas for the rest of your career, and you might be seeing these Anova tables or F-tables. Just to remind you, an Anova is an analysis of variance, and this analysis of variance is a statistical test put together by Fisher many, many decades ago, and so we call the F-test the Anova. F is the Fisher test, and we'll get some practice looking at the F-tables here. This is one that we had seen before, but what I'll do now is ask you a series of questions that really get you to move inside and outside of these tables and see if you can work your way around them. So here's a sample F-table. What are the other names for these two terms? The term right here and the term right here. We'll let you think about that for a moment. Okay, hopefully you've thought that through, and I will give you the answers on these in this video today. Here I'm going to tell you that, as you might recall, this will be the between groups variability. This would be the within groups variability. We sometimes simply refer to this as the group effect, and this would be the error term. But you can think of this as between versus within. Okay, let's move on and go to our second question. We have a total of 7 of these, and this is the second of 7 questions about this F-table. According to the F-table, should we reject or retain the null hypothesis? We'll let you think that through. Okay, hopefully you are inclined to reject the null hypothesis, and the reason is right over here. One of the mantras that you should know by now is that if the observed alpha level is below 0.05, we reject. We can also say that slightly differently. If the sig value is below 0.05, we reject. And here we have a sig value that is 0.0019. So hopefully that's clear to you, and something that's not too familiar. We've introduced that even as far back as our days in discussing chi-square. Let's go on to our third question about the F-table. According to the F-table, does the study have validity? We'll let you look over the F-table, think that through. Okay, well, welcome back. And what I should confess here is that that was a little bit of a trick question. There really isn't any information in the F-table that can tell us about validity. Validity is a very difficult idea. It's a very complicated and multifaceted notion. There's internal validity. Are we measuring what we want to measure? There's external validity, the extent to which our observations and our conclusions might generalize to novel populations, to novel situations, novel stimulus conditions, and so forth. That's external validity. We can also think about other kinds of validity that we've introduced. When we were constructing our surveys, we talked about trying to establish convergent validity and discriminant validity, the extent to which our instrument is converging with other measures of the same construct. That would be convergent validity. The extent to which our instrument is measuring something that is distinct from a similar yet slightly different kind of construct. We want to be able to establish that we have discriminant validity. So there are many different kinds of validity. We have our R statistic that is used to help us with that. The Pearson R statistic is especially helpful for these kinds of judgments. But there's nothing about the F-table per se that tells us about internal validity or external validity. We'd have to come to conclusions about validity using information that goes far beyond the F-table. So the point of asking that question was to get us to realize that the F-table doesn't tell us everything, although it tells us many things. Okay, let's go on to our next question. According to the F-table, how many groups were there? We'll let you think that through. Okay, and if you're ready to return, we'll come back to the idea that the answer here is 4 groups, And the reason that we come to that conclusion would be based on the notion that the number of degrees of freedom is always equal to the number of groups minus 1. So we have here 3 degrees of freedom, which would imply that the number of groups had been 4, because 4 minus 1 gets us to 3. So if we understand how the degrees of freedom are computed, then we can begin to look at an F-table and draw out a lot of information about the study that had been conducted. Let's go on to our next question. According to the F-table, how many participants were there in each group? And we are going to stipulate here that we have equal n. That is, we had equal numbers of people in each of the 4 groups. Okay, so we'll let you work that on through. Okay, and again, hopefully you're able to come to the number 5. That is, there were 5 people in each of the 4 groups, and here's how we might think about that. A moment ago, we had already concluded that there were 4 groups. Okay, and you might remember from a prior lecture that we had computed the degrees of freedom down here for the error term, the within subjects component, as being the total number of observations minus the number of groups. Since we have 16 as the degrees of freedom, and we know that we have 4 groups, we could say that we had a total of 20 people in the study. And because we had 20 people in the study, and because we had 4 groups, all of which were equally sized, we would have a total of 5 people in each of our 4 conditions. So none of the arithmetic in that particular question was too difficult. We're simply multiplying some numbers together or dividing. These are relatively simple arithmetic operations. On the other hand, trying to understand where these numbers are coming from does require some quantitative reasoning. Okay, let's go on to our next question. According to the F-table, which groups, if any, differed significantly from each other? We'll let you think that one through. Okay, and what we can say here is that this is, again, a little bit tricky for the following reason. On the one hand, we know that we have a statistically significant finding. Using our earlier song from Sesame Street, we can say that the F value here is telling us that one of these things is not like the others. We have at least one difference somewhere in our set of means. Having said that, we actually don't know which of the means would be different from which of the other means. We don't have any information available in this F-table. We can think of the F-table as being an indication of what we called earlier the omnibus F. That's the overall analysis. There's at least one mean that's different, but we don't know where that one might be. We might have to do something like a post hoc test to pinpoint that difference, and at the same time we might choose to control for cumulative type 1 error. But that information is not available in the F-table. Okay, let's go on to our next question. According to the F-table, which was greater, the variance between groups or the variance within groups? We'll let you think that through. Okay, welcome back. Let's see if we can get to an answer. So what we can say is that variance we've defined before as being the sums of squares divided by the degrees of freedom. Even from our earliest weeks of class, we had made that kind of a computation. Again, the variance is equal to the sums of squares divided by the degrees of freedom. So inside of the F-table, we can take this 54.55, for example, divide it by 3, and we come up with the variance for the between subjects component. We can repeat that exercise, sums of squares divided by degrees of freedom, down here for the within subject component, also called the error term, and we come up with the variance for the error term. And our synonym for the variance is the mean square. That's something that we had introduced in the last video, but we want to make sure that we're really driving that point home now. So the variance is a mean square. And we actually need 2 mean squares inside of the Anova. We need one for the between subjects component and one for the within subjects component. So here we can see that the variance for the between subject component actually is larger than that for the within subject component, 18 versus 2, essentially. Forgetting about the rounding just for a moment. That would be one way to answer this question. There's another way to answer this question, which was equally legitimate, and that is to look very simply at the F ratio. Remember that the analysis of variance is a comparison, a ratio of 2 variances, and that's the between subject variance over the within subject variance. Consequently, if the F ratio is exactly 1, then those 2 variances are identical to each other. On the other hand, if we have a relatively an F value that is larger than 1, then we know that the numerator's variance, in this case the between subject variance, would have to be larger. On the other hand, if we have an F value that's smaller than 1, then we know that the denominator must be larger than the numerator. That is to say, the within subject variability must be greater than the between subject variability. So a couple of different ways to get to that same conclusion. Okay, let's go on to our next question. According to the F table, was the homogeneity of variance assumption satisfied? We'll let you work on that for a moment. Okay, welcome back. And this is an opportunity to remind you that each of our parametric tests, whether it's an R statistic, a T statistic, or the F statistic that we're using here, does depend on three different assumptions. One is the normalcy assumption, that is, we assume that the data are normally distributed. We also have an equal variance assumption, which is what we're dealing with here. Finally, we have the independence assumption. Regarding that second assumption, the equal variance assumption, which some statisticians would say is the most important for evaluating in Anova, we actually can't tell by looking at this F table whether we have equal variances or not across our groups. We would have to take a look at something called the Levine test. More specifically, we would have to look at the sig value associated with the Levine test, and we would use the rejection rule that we always use in our class, and that is that if the sig value is less than 0.05, we reject. In this case, we would be rejecting the equal variance assumption. For the moment, though, all we have is the F table, so we don't have any information about the Levine test or the equal variance assumption, so the F table doesn't allow us to answer that question. Okay, I hope you found that helpful, and I hope that gave you some guidance as to what kinds of information is directly available in the F table, what kinds of information can be derived by knowing something about how the F table is computed, and then what kinds of information is actually beyond the bounds of the F table. It's not there directly, nor can it be inferred from the F table. A little bit of practice on that, I think, will go a long way. Okay, let's see if we can further develop our understanding of the computations that are represented in the F table. And in each of the following F tables, I'm going to omit some information, and we'll see if you can fill in the missing information. Being able to do that will show us you have some mastery of how the F table is operating, and more importantly, some mastery of the quantitative reasoning that's going into these kinds of data analysis techniques. So here's an F table, and we have a source of variation. We have the sums of squares, as always. Right next to that, we have the degrees of freedom. We have the mean squares, which we said were simply variances. And then we can get our analysis of variance, which is our F ratio. And also we have a p-value. In this particular case, our p-value, also known as our sig value in many software packages, is missing. So is the F ratio here significant? And you can feel free to use some Excel tricks to do that. We'll let you stop the video and give that a try. See if you can fill in that missing p-value. Okay, welcome back. I'm going to join you now. I'll break out of this just for a moment. I'll make that a little bit smaller and off to the side. And I will go into Excel and show you how you might have been doing this. Maybe some people were successful in figuring this out, others less so. So the piece of information that we need is the p-value associated with the observed value of f. In this case, it happened to have been 14. So you might remember a couple of our Excel tricks when we've done t-tests before and we've done chi-squares before. We've used the INV functions, or the inverse functions. And correspondingly, we've used the DIST functions, or dist functions. And remember that the INV functions are used when we want to obtain the critical value. That's the value of the statistic that we would have to beat or exceed in order to reject the null hypothesis. Alternatively, what we can do is use the dist functions to obtain the observed value of our alpha level. The observed alpha level would have to be lower than 0.05 for us to reject. So let's take a look at the information that we have here. We can see that we have some degrees of freedom listed, 3 and 21. We can see that we have an F ratio that's listed, and that's probably all we need to use to complete our dist function. The dist function, again, gives us the observed value for the alpha level. So let's go ahead and do that. And here we're going to use, for the first time, the Fdist function, just like we used to use the chi-dist and the t-dist. So I'll now put in Fdist. I'll open a left parenthesis, and the computer prompts me for the observed value of f. A little bit counterintuitively, it asks us with an x rather than with an f, but that observed value is 14. I'm going to plug that in. And then it asks us for the 2 degrees of freedom. In an earlier video, we had given you a heads up that what we want to do with the degrees of freedom is always insert the degrees of freedom for the between subjects component. That's our numerator's degrees of freedom. And then subsequently, we'll insert the degrees of freedom associated with the denominator, that's our error term, equivalently our within subjects or within groups component. So why don't we go ahead and do that? We get 3 degrees of freedom for our numerator, and here I'm getting the 21 degrees of freedom for our denominator. So in its entirety we have equals. We're using the Fdisk function to pull out the observed value for our alpha level. We observed a 14 F ratio, or F ratio equaling 14 with 3 and 21 degrees of freedom, and if we hit enter now, we get a number like this. Hopefully if you're doing this in Excel, you're getting that same number. And this is a very intuitive number to some of our students. It's a less intuitive number to some other students. Here we're getting a number that's expressed using scientific notation. So I know you're only watching a video, but raise your hand if you've seen scientific notation before. As you might remember, what we're doing in scientific notation is we're taking advantage of exponents. And in this particular case, we're expressing this number as 3.08 and some change raised to an exponent that has a value here of -5. That means that we have to make this now smaller by essentially 5 log units, or 5 factors of 10. So we're going to go over here once, twice, 3, 4, 5 times. We'd have all these leading zeros before we finally got to that 3. That's what this -5 is telling us to do. Stated more simply, we have an observed alpha level that's far, far lower than the 0.05 alpha level, which is our criterion alpha level. So clearly, this number is going to be something less than 0.001. It's quite a bit lower than 0.05, and we can reject the null hypothesis. We did all that because we took advantage of the F ratio, the degrees of freedom, and our newfound Fdisk function. Okay, let's go back over to PowerPoint and we'll take a look at the next problem. The next problem is shown here, and we see a lot of similar information, but as you can tell, the central row is missing all of its information. We have everything that we need about the between groups row. We have our grand totals, which isn't even always necessary inside of an F table, but sometimes that information is provided. And then we have some missing information here for the within groups components. We'll let you take a moment, stop the video, and see if you can fill in these missing 3 question marks. Okay, welcome back. Why don't we see if we can begin to understand how we might fill these in? What we can say is that we have some information already for the between groups conditions, and then we also have the information for the totals, and that might prove to be helpful. For example, you can see that we have a total of 42 for our sums of squares. We can also see that 42 of the, out of those 42 units, 35 of the units are coming from the between groups component, and since the total would have to be equal to the sum of these two, we can simply do 42 minus 35, giving us the missing 7 units. This number would have to be a 7. We can use that same logic for the next column over. This would be the degrees of freedom, and we can take our 9 units, which is what we have in total. We know that 2 of those 9 units are already coming from the between groups component, and so these 2 units must need to be added to 7 more to get up to 9. That is, 9 minus 2 would get us to 7. So far, we have a 7 over here, and we have a 7 over here, and then we could go to the missing component, which is the mean square. And the mean square, as you might remember, is always sums of squares divided by the degrees of freedom. So in this case, we would do 7 divided by 7 gives us 1. So we have a very simply computed mean square value of 1. Just to make sure that's really clear, we can look at the example that we have immediately above in the between groups row. We have 35 divided by 2 gives us 17.5. Here we'd have 7 divided by 7 gives us 1. There's one other intuition that you might have had. There are lots of different ways of filling out the missing information here. You might notice that the mean square between was 17.5. And similarly, the F ratio was 17.5. We know from our earlier video that the F ratio is actually equal to the mean square between divided by the mean square within, and since we're getting 17.5 in the 2 cases, the only number that would make that true would be the number 1 right here. 17.5 divided by 1 would give us 17.5. So a couple of different ways to come to that conclusion. Okay, let's go on and see if we can do another problem here, filling in the missing information for the F table, and in this case what we're missing is this F ratio. We'll give you a moment to try to compute the missing information. Okay, so what we have is the F ratio is missing, and as we've said a few times, the F ratio is always equal to the mean square between divided by the mean square within. So we're going to be doing 5 divided by 1.5. I'll break out of here just for a moment and do it with you inside of Excel. This will be equal to 5. And so we understand where that's coming from conceptually. That's going to be the value of the mean square between. We'll divide that by the 1.5 mean square within. And we wind up with an F ratio equaling 3.33. Okay? And so this value should be 3.3 repeating. Okay, why don't we go on and do one more? In this particular case, we now have an entire column that's missing. All of our sums of squares are missing, but everything else is in place. Okay, so why don't we see if you can take a moment and recover that missing information. Okay, welcome back. Let's see how you might have thought about this. So a couple of different ways to go, but I think maybe the most straightforward way to go is simply to remember how the mean square is computed. The mean square is a variance. And as we learned in our earliest weeks of class, the variance is simply the sums of squares divided by the degrees of freedom. So some number, which is currently missing, divided by the degrees of freedom, 5 in this case, gives us 40. What we can do is try to recover this just by using that very simple algebraic manipulation of moving the terms around and recognizing that we can multiply the mean square, which is the variance, times the degrees of freedom to recover the sums of squares. So let's break into Excel and just do that. I realize that some people here can do that in their heads. In this particular case, we'd have a variance of 40 times 5 degrees of freedom. I'll now put 40 times the 5 degrees of freedom, and we wind up with a sums of squares of 200. If you prefer to check your work, 200 divided by 5 would give us 40. So hopefully that makes sense. And we can do the same thing down here as well. Take 20 times 45. Let's go ahead and put that in. Equals 20 times 45. And that would be 900. So 900 divided by 45 gives us 20. We're simply undoing the operation that we did a moment ago. So we had 200 and 900. That would equal to a total of 1100 over here. Hopefully that's clear. Okay. All right, so now we've gone through some F-table exercises, and we've hopefully developed in you some intuitions about how the F-table works, where all those numbers are coming from, and hopefully you've got some intuitions about what the numbers mean. It's not just an arithmetic computation or a matter of clicking on the right menu items. You really understand the quantitative reasoning behind these values. Why don't you stop the video right now and make a note of what has been clear to this point and what has been less clear. Okay, welcome back. What we'll do now is introduce something that's entirely new. We'll be talking about something called the basic ratios, and we'll be looking at basic ratios throughout most of the rest of the semester. Here we're introducing the basic ratios in the context of the between subjects ANOVA, and specifically in the context of the one-way between subjects ANOVA. So let's go into some of these details, and then we'll get some practice also in class. One can calculate the F ratio by finding variances lots of different ways. There are many different ways of computing an ANOVA, or an F ratio. There are different methods that are all algebraically equivalent to one another. One method that some people believe to be generally the easiest, and it might not seem really easy to you, but it's one of the more straightforward ways, and it's a very flexible way, involves computing these basic ratios, which are special quantities that allow for simpler manual computations of the ANOVA. We're going to be having the computer help us compute do all the calculations for the ANOVA, but sometimes we're going to compute them by hand, so to speak, inside of Excel, and we'll use basic ratios in order to do this. Okay? So each of the basic ratios will be signified by an arbitrarily chosen letter, and the 3 letters that we're going to be starting out with this semester will be Y, A, and T. Those letters don't particularly mean anything. They're just placeholders for us. When we want to signify that this is a basic ratio, we put these capital letters inside of brackets. So that's what those are, Y, A, and T. And we're going to take a look at each of these basic ratios in just a moment. Before we do that, though, I want to make sure that we're fully motivated in understanding why we use these basic ratios. So what I'd like to do is break out of this just for a moment. And I want to give you a mantra for today. This might turn out to be a really good pop quiz question also. Our mantra for today speaks to the issue of why we bother with basic ratios. What's our motivation for doing them in the context of ANOVAs? So let's see if we can get our mantra down. Our mantra is basic ratios help us compute the sum of squares. Okay? Can you say that with me? Basic ratios help us compute the sum of squares. And these are three of the basic ratios that we're starting out with today, y, a, and t. Those are arbitrary letters. The brackets indicate that they are in fact basic ratios, but if we are going to be computing ANOVAs, one of the first things that we have to do in our F table is get the sums of squares. And that's actually a fairly difficult thing to do, but the basic ratios will help us compute those sums of squares, and that's our motivation for learning these. So please say it with me one more time. Basic ratios help us compute the sum of squares. Ah, there it is. I knew you could do it. And again, that might turn out to be a pop quiz question in class. Okay. So now let's go in and see if we can understand inside of PowerPoint what these basic ratios might look like and how we would compute them. We're going to introduce three of these, the first of which is called basic ratio y, and this is a basic ratio that's going to give us some information related to individual participants. Okay? So here's the basic ratio y, and here is how we would compute this. I will not ask you to memorize these formulas, but I will ask you to be able to compute them if the formula is given to you. So here's the formula, and what we're going to do is we're going to take the individual scores, and we're going to square the individual scores, and then we're going to sum those up. And that's stated right here. The sum of the individual squared scores, square them first, then sum them. And this is a fairly common mistake. People will get the order of operations done incorrectly. And to help you remember that, of course, we have that acronym called PEMDAS, or Please Excuse My Dear Aunt Sally. What that means is that we take parentheses first, that's the P in PEMDAS, and then we do exponentiation next. That would be the next level in our hierarchy. After that, we have the M and D for multiplication and division. That would be the level of or the sequence of operations after we've already completed the exponentiation. And then in the lowest level of the hierarchy, we have simply addition and subtraction. Here, you can see that we have to exponentiate first, and then we're going to add later. So we're going to square them first, then sum them. Okay? Let's see if we can take a specific example. How might this look inside of Excel, or maybe even inside of SPSS if we had a spreadsheet that contained our data? We'll assume that we're running a study that has three groups. Okay? Earlier we talked about a study where we were interested in cholesterol levels for young adults like you, middle-aged adults, and older adults. This might be a health psychologist who has a developmental slant. That is, they want to see how cholesterol levels change across the adult lifespan. So we might have measurements from three different groups. These don't look like cholesterol levels, but I think you get the point. And what we're doing here is we're basically taking these raw data, and we're creating a similar structure inside of Excel, something that occupies the same amount of space, same number of rows, same number of columns, and we're going to say that the value in any one cell here for our squared scores will be equal to its corresponding value up here squared. So we're going to take that 3 and square it, and that'll give us 9. 6 squared gives us 36. 7 squared gives us 49. 4 squared gives us 16. 5 squared gives us 25, 7 squared gives us 49, and so on for the remaining two columns. So inside of Excel, this value, genotypically, would be equal to that squared. And we can use the exponentiation sign and the squaring to make that happen. Okay? And then we can do that for all the values here, all the values here, and once we have all of those squared scores, we then sum them up, and we wind up with our y basic ratio. Okay? All right, let's move on to the second of our three basic ratios, and this would be the basic ratio A. The basic ratio for groups or conditions is called A. In the between subject case, we think of these as being different groups. So far, we've looked at the individuals with basic ratios, and that was our y component, or our y basic ratio. Here we're getting the basic ratio A. This one's a little bit trickier. What we're going to do is we're going to be summing up some totals and squaring those totals, and we'll do that for each of our three conditions. The conditions here are signified by the lowercase a. So if we have a equals 3, then we have three different conditions, and we'll do this once for the first condition, once for the second condition, once for the third condition. Each of those conditions would be a different group in this case. So here we are, the basic ratio A is equal to the sum of the squared column totals divided by the number of subjects per condition. The lowercase n would be the number of subjects per condition, and here we're using a simplifying assumption that we have the same number of participants in each of our conditions. Okay? Each column total corresponds to a different level of the IV, and we have A such levels. In this case, we might have 3, as you see here. So here are the raw scores for the people who are in groups 1, 2, and 3. You might also notice that we have 1, 2, 3, 4, 5, 6 persons, or 6 participants anyway, in each of these 3 groups. Okay? So what we can do is take a grand total of those 6 scores. That would give us 32. And let's make sure you're following that. 3 and 6 would get us to 9. 9 and 7 would get us to 16. And then 4 more would get us up to 20. Here's 5 more getting us up to 25. And 7 more would get us up to 32. We'll take the 32 and square it, and we get 1024. And that's our squared column total. We'll do the same thing for group 2 and group 3. We'll take each of these numbers down here. Okay? And now we have the squared column totals right along our numerator, and we'll divide by the number of observations that we have in each condition. That was lowercase n. Okay? And that's going to give us our basic ratio for A. Okay, we'll move on now to our third and final basic ratio, at least for today's conversation. In future conversations, we'll have additional basic ratios, but we'll always be building on the y, a, and t that we've introduced today. So here's our final basic ratio, and this is the one for the grand total. It's called t. As always, it's a capital letter inside of brackets. And what we're going to do is take the grand total of all of our scores summed together, and we're going to square that, and we'll divide that by capital N. Capital N is the total number of participants in the entire study. Not just one condition, which would be lowercase n, but the grand total of all participants. Okay, so the grand total is squared and then divided by the total number of scores. We'll sum them first, then square them. The total number of scores, n, and that's the capital N, is equal to the number of conditions that we have, signified by A, times the number of participants that we have per condition, lowercase n. All of these formulas are working with a simplifying assumption that we have equal numbers of participants in each of our groups. In this case, we're using 3 groups. Okay, let's see if we can see where those numbers are coming from. So what we can do is take a sum of all of these, and that would be 92. And you can do that in Excel by saying equals sum and highlighting over these 6 values across the 3 groups. Alternatively, you could take the sum this way by adding the column totals, and you'd wind up with 92. What we want to do is square the 92. That brings us up to 8,464. And then we're going to divide that by the total number of participants that we have. In this case, we have 18 participants because we have 1, 2, 3 groups, and we have 1, 2, 3, 4, 5, 6 participants per group. Okay, so that's the grand total squared, 8464, divided by 18, gives us our third basic ratio, and that's the basic ratio for the grand total. That's called t. Okay, so far now we've gotten the values associated with 3 different basic ratios, and remembering our mantra, these basic ratios are going to help us get the sums of squares. The sums of squares will appear in the leftmost component of our F table. And what we can say also is that these basic ratios will help us to build up the other components of our F table simply by virtue of the fact that they get the sums of squares going. The sums of squares would be our starting point. Okay, these are flexible in the sense that we can use these for between subject analyses like we're doing this week. In future weeks, we might be doing within subject analyses, and we can use basic ratios there again. This week we're talking about a one-way Anova, which is to say that we have one independent variable that would have at least 2 levels and most likely more than 2 levels. But in future studies we might be talking about factorial or complex designs which have multiple independent variables, each of which will have at least 2 levels and sometimes many more than 2 levels. All that complexity can be simplified computationally by taking advantage of these basic ratios, the first 3 of which we've seen today. So let's see now if we can take what we've learned today and put them into an F table. We're going to look at an F summary table, and where we used to have these sums of squares, we'll see that we now have some basic ratios. This will be a handout that you'll get in class. This should be a very familiar looking F table to you now. We have the between subject conditions, the between subject variability in the first row. Beneath that, we have the within subject or error term. Within subject variability or the error term. And as always, sums of squares, degrees of freedom, mean square, and F ratio, as we did earlier in today's video. What we can say, though, here is now we can begin to take advantage of our basic ratios. The basic ratio for the between subjects condition would be A minus T. That would give us the sums of squares for the between subjects conditions, between subject variability, and then we have the error term, or the within subject variability, signified by the basic ratio y minus a. So once we've computed those, all we have to do is mix and match them by doing some differencing. That will give us the sums of squares. We can divide that by the degrees of freedom to get the mean square, which is a variance. And then we take the ratio of two variances, mean square between over mean square within, and we have our F ratio. Okay, so what we'll do is, time permitting in class, we'll get into some computations on a computer software package like SPSS, and we'll actually have the computer do all of that work for us. We'll also spend some time in class computing these basic ratios so that they're familiar to you. What I'd like you to do now is work on your metacognition. Think deeply about what it is that you do understand, and also what needs greater clarification. Make a note about all of that, and bring that into class. See you in class.